Differential and integral operations 12. Prove these integral forms of the differential operators. Gradient of phi is limit as the area and volume go to 0, closed surface area phi d sigma divided by the volume integral theta. Now let's recall the gradient operator. So gradient operator applied to a scalar function phi gives us del phi del x in ex hat direction plus del phi del y in ey hat direction plus del phi del z in ez hat direction. Okay, now let's consider a small volume which is defined by this cube and that has 6 faces, and we're going to consider the area that corresponds to the surface 1. Now you can see that for this one the area is delta x multiplied by delta y, and the normal vector is defined to be perpendicularly outward direction. So this is in minus ez hat direction. So let me write for S1, I have the area vector delta sigma 1, which is delta x, delta y in minus ez hat direction. And for S2, the second surface, the top surface, it's again delta x, delta y, this time in plus ez hat direction, delta x. So delta sigma 2 is delta x, delta y in plus ez hat direction. And for the surface 3 is the back surface here, the blue one. It is delta y multiplied by delta z, delta y, delta z in minus ex hat direction. So it's normal to the surface in the outward direction. Delta sigma 3 is delta y, delta z in minus ex hat direction. And for surface 4, which is the front surface here, it's delta y, delta z in plus ex hat direction. So delta sigma 4 is delta y, delta z in plus ex hat direction. For surface 5, that's the left surface here. It is delta x, delta z in minus ey hat direction. Delta sigma 5 is delta x, delta z in minus ey hat direction. And for 6, it will be delta x, delta y in plus ey hat direction. Okay, so let's do surface 6. Surface 6, I have a delta sigma vector, which is delta x, delta z in plus ey hat direction. So that is delta x, delta z in plus ey hat direction. Now I'm ready to write this closed surface integral. So the closed surface integral S phi, my scalar function d sigma, is on surface 1, it is minus phi, because this is a small area, it's phi xyz approximately, multiplied by delta x, delta y in EZ hat direction, and then I have plus phi. This time I'm on the top surface, so it is xy, but z is z plus the delta z, and I have delta x, delta y in EZ hat direction. Now for the third surface, I have minus phi, the scalar function phi, which will be evaluated at x, y, z, delta y, delta z in EX hat direction. That's surface 3. For surface 4, the front surface, I'm at x plus delta x. So this will be plus phi evaluated at x plus delta x, y, and z, delta y, delta z in EX hat direction. And for surface 5, I have minus phi xyz, delta x, delta z in EY hat direction. And then I'm going to surface 6. Surface 6 is here. I moved on the y-axis to y plus delta y. So this will be phi evaluated at x, y plus delta y, z, delta x, delta z in plus EY hat direction. On the other hand, what is the volume integral d tau? It is delta x, delta y, and delta z. That's the volume of the cube. Now, what is the limit as v goes to 0? Delta x, delta y, delta z, they become differential lengths dx, dy, and dz. All right, so let's put it together. The limit as s and v go to 0, the closed surface integral phi d sigma divided by the volume integral d tau is equal to the first term phi. I have the positive term here is let's write this term x plus delta x y z minus x y z, x plus delta x y z minus phi evaluated at x y z in EX hat direction. This will be divided by dx and plus I have phi this time at x, y plus delta y, z minus phi at xyz in EY hat direction divided by dy plus phi evaluated at x, y, z plus delta z minus phi x, y, z. Now remember that I have taken the limit as v goes to 0, so this becomes dx, this becomes dy, and this becomes dz. So these are infinitesimal lengths divided by dz in ez hat direction. So that's the situation because I have delta x, delta y canceling out. I'm left with delta z for this term. And for this term, for x plus delta x, delta y, delta z cancels out. I'm left with delta x, which becomes dx. And for y plus delta y term, delta x, delta z's cancel. I'm left with delta y, which becomes, for this term, it becomes dy. So here, all of these lengths, dx, dy, and dz, are infinitesimal. So let me write here dx, dy, dz, infinitesimal. Okay, so what do I see here? The first term here is the derivative of phi with respect to x in the limit delta x goes to 0. So this is del phi del x ex hat. The second term is del phi del y ey hat. And the last term is del phi del z ez hat, which is the gradient of phi. This is the gradient of our scalar function phi. Therefore, we have reached the conclusion that this statement is correct. Okay, so let's go over what we did here. Gradient of phi, the integral form of the differential operator definition, limit s and v goes to 0, closed surface integral phi d sigma over the volume integral d tau. Now I'm considering an infinitesimal volume, delta x, delta y, delta z, and for the volume going to 0, this becomes dx, dy, dz. And the area becomes 0, becomes, instead of, for example, for surface 1, delta x, delta y, it becomes dx, dy. So that's the meaning of S and V going to 0. So first I write the area vectors for the infinitesimal area vectors for each surface. For example, this one is delta x, delta y in minus ez hat direction. The normal vector is defined perpendicular to the surface in the outward direction. So I did that for all these surfaces. And then I have written the wave function, the scalar function phi at these surfaces. On surface 1, the bottom surface, phi is evaluated at x, y, and z. On the top surface, it is evaluated at x, y, and z plus delta z. For the blue surface, which is the one at the back, it's evaluated at x, y, z. For the front surface, it is evaluated at x plus delta x. For the fifth surface, it's x, y, z. Sixth surface, we are at y plus delta y. So I've carefully taken that into account. and I have written the d sigma vectors properly, and then all these uh, small lengths have become infinitesimal when I take the limit s goes to 0 and v goes to 0. So this becomes phi of x plus delta x plus dxyz delta y delta z divided by dy dz divided by dx dy dz. These cancel, so I'm left with dx. Similarly for this one, and I do this for all the terms, and limit as x goes to 0. This is the definition of derivative, so that's the partial derivative of phi with respect to x ex hat, y with respect to y ey hat, and with respect to z ez hat, which is indeed the gradient of phi.